Previously, we looked at the hype cycle, and we demonstrated that our goal for this class is to help you move along that hype cycle curve so that you can really understand AI and start rising towards productivity in it. You don't have to be a programmer or a developer to be a part of the AI revolution, but I do think you have to understand the fundamentals of how it really works and what it really is. To that end, we spoke a little about programming and about how traditional computer programming is when a developer comes up with the rules to solve a problem, implements those rules using a programming language, and a computer then executes those rules. This is used everywhere from gaming to financial services, medicine, and medical systems, and a whole lot more. The innovation that led to the AI revolution was to use computing power to figure out the rules instead. So, with lots of data, we could do a pattern matching to figure out the answer to a problem. So in the example of tic-tac-toe, we could represent the board like this and tell the computer that if it's playing as O, that if the board looks like this after their next move, then they're going to lose. And if it looks like this after their next move, then they won't lose, they might even win. Or, for a more useful case, if we have an ophthalmologist say that this retina demonstrates diabetic retinopathy, and so does this one, and this one, but these ones don't, then a computer can match this raw information and come up with a computer vision AI model that can be used to help diagnose the disease. But when you use this method, you can actually go further than a human may be able to. So consider this example, where we know the age of the person who owns this retina, as well as all of these. And then, using the same technique of pattern matching, we could train an AI to predict a person's age based on their retina. Now, this was something that was built at Google, and it has a mean average error of about 3¼ years. So that means that the model, when shown a picture of a retina, will usually predict the person's age to within 3¼ years, and no human can do that. But as I mentioned, to do this, you need lots of data and lots of examples. So let's look at a case of how that might work and some of the things you need to know when gathering and preparing your data. In this slide, I have lots of pictures of various items of clothing, and to you or I, they're very recognizable. And if I were to ask you to pick out the shoes, you'd probably identify these. My first question would be, well, how did you do that? How did you, for example, determine that this shirt wasn't a shoe? In your mind, you have experience, and you just know that it isn't. But how would you teach that to a computer? How would you teach that to an intelligent being that has no idea what either a shoe or a shirt is? A part of this is you would identify features. So if it has a collar, it's not a shoe, for example, or at least very probably not a shoe. But things start to get really complicated if you start trying to come up with rules like that. So let's simplify. Let's instead show a computer lots of examples of shoes and let it know that these are shoes. Now imagine if you've never seen what a shoe is, you have no idea what a shoe is, and I told you that all of these are shoes. In your mind, you'd picture what a shoe actually is based on the shape and maybe things like laces, soles, and all that. It would give you a pretty good idea of what a shoe is. But then I show you this. We know it's a shoe, but in my hypothetical situation of training somebody who's never seen a shoe before, and they only had what I showed previously as examples, well, this high heel shoe would look pretty alien. This is a concept in AI that we call overfitting, where, for example, if you train a computer on a set of examples of shoes that only look like hiking boots, then you don't have broad enough data for a model to be smart enough to understand that a high heel shoe is still a shoe. And this is a very important concept when you take a journey into understanding AI. Your models can only be as smart as the data used to train them. And it's very easy for you to introduce bias into your data at an early stage. And while the example of a high-heeled shoe not being recognizable as a shoe is a relatively harmless and trivial one, what if your model makes decisions that could impact people's lives? And what if the data you use could treat one class of people differently than another? It could be easy for you to programmatically reinforce or introduce a negative stereotype, and it's something that you need to be aware of when creating systems. So, to recap, entering the realm of AI and machine learning involves starting with lots and lots of data. The programmers will have tools that match that data to answers about it, like matching an image of a retina to somebody's age, or a game condition to win or loss, or a picture to whether it's a shoe or not a shoe. And before you can do this, like I mentioned, you need a lot of data, and you need to make sure that the data is sufficient to cover your scenario. So the first question people usually ask at this point is, well, how much data do I need? And the answer, to be honest, is that it depends on your scenario. But I'd encourage that before you consider the volume of data, you should also consider the breadth of data to make sure that you have examples of every type of item you want the computer to be able to learn about. Sometimes we say 10,000 items of data is enough. You might think you have enough with 10,000 items, but you haven't covered most of your classes. You might be better with less data with broader coverage. And so as a result, if you do that, the volume of data will generally look after itself. Now that you've learned to understand the importance of data, the next step will be to get a little hands-on and play with a tool that captures you posing your hand as rock, paper, and scissors, trains a model with that data, and then learns to recognize your hand pose.